Now, let's move on to another important type of electric field problem. In this example, instead of a point charge, we have a continuous charge distribution along a uniformly charged rod. If we look at the figure, the rod has a total charge Q and a length L. Our goal is to find the electric field at point P, which is located a distance A from the left end of the rod. Before we begin the solution, let's introduce an important concept. Since the charge is uniformly distributed, we define the linear charge density denoted by lambda. Linear charge density is simply the charge per unit length, and it is given by lambda equals Q divided by L. Next, instead of considering the entire rod at once, we select a very small element of the rod with length dx. The charge contained in this tiny element is dq equals lambda times dx. Now, let's solve the problem step by step. Step 1. Write the expression for the electric field produced by the small charge element dq. From the figure, r, distance between dq and point P, is x plus a. Therefore, dE equals k times dq divided by the quantity r squared. Now substitute dq equals lambda times dx and r equals x plus a. This gives dE equals k times lambda times dx divided by the quantity x plus a squared. Step 2. Since every small electric field points in the same direction, we simply add all of them by integration. Integrate from x equals 0 to x equals L. This is a very useful formula to memorize. You know, sometimes we simply have to memorize a few important equations. This is definitely one of them, because you'll use it repeatedly in continuous charge distribution problems. After evaluating the integral, we obtain k times lambda multiplied by the quantity 1 over a minus 1 over the quantity a plus L. Finally, substitute lambda equals Q divided by L into the equation. After simplifying, we obtain the final result. The electric field equals KQ divided by A multiplied by the quantity A plus L. At this point, one question students often ask is, how do we know the direction of the electric field? That's a great question. Let's look at the figure. The rod is positively charged, so every small charge element dq is also positive. If we place a positive test charge at point P, each charge element repels it. Therefore, every small electric field points away from the rod, which is toward the left. Since all the small electric field vectors point in the same direction, we simply add their magnitudes, and the net electric field also points to the left. This is the standard expression for the electric field on the axis of a uniformly charged rod, and an important result to remember for exam problems. Now let's continue with another important electric field problem. This example is very similar to the rod problem we solved in a previous lesson. The main difference is that the charged rod is now semi-infinite. Instead of having a finite length, it starts at y equals 0 and extends all the way to positive infinity. Because of this, the upper limit of integration changes from L to infinity. Now let's solve it step by step. First, choose a very small element of the rod with length dy. Its charge is dq equals lambda times dy. From the figure, the distance between this element and point P is r, which equals the square root of r squared plus y squared. Using Coulomb's law, the magnitude of the small electric field produced by this element is k times lambda times dy divided by r squared plus y squared. Now let's continue by resolving the electric field into its components. The horizontal component is DEX, and the vertical component is DEY. Using the geometry shown in the figure, we obtain the component equations displayed on the slide. Now we integrate both components from y equals 0 to positive infinity. After evaluating the first integral, we obtain EX equals k lambda divided by r. The second integral gives the same result, so EY also equals k lambda divided by r. And here's a quick tip. This integral is another very important one. Just like the formula from the previous rod problem, it's definitely worth memorizing because it appears frequently in electric field questions. Now we can calculate the magnitude of the electric field. Since EX and EY are equal, the magnitude becomes square root of 2 times k lambda divided by r. Finally, let's find the direction. Using the tangent relation, tangent theta equals EY divided by EX, which equals 1. Therefore, theta equals tangent inverse of 1, giving 45 degrees. So the net electric field points 45 degrees below the positive x-axis. That completes this example. If you enjoyed this lesson, don't forget to like the video, subscribe to the channel, and share it with your friends.